Hello class, today we're going to be continuing discussing the simple harmonic oscillator, but this time discussing average values of potential and kinetic energies. And we're going to begin by showing the difference in how different models handle potential and kinetic energies. So we'll begin with going back to the particle in a box model, which makes use of the Schrödinger equation, h psi equals E psi, where h is the Hamiltonian operator, and that is equal to the kinetic energy plus the potential energy. So we haven't seen this version of the Hamiltonian in a while, probably not since chapter 2, but the Hamiltonian operator operates to produce the energy eigenvalue, and it is composed of kinetic energy based on x and potential energy based on x, which is why the Hamiltonian operator is often referred to as the total energy operator. Now, for the kinetic energy, we derived an equation. So Hamiltonian operator would be equal to negative h bar squared divided by 2 times the mass times the second partial derivative with respect to x plus the potential energy based on x. When we were dealing with the particle in a box, the walls were potential energy equals infinity. And so inside the box, the potential energy was equal to 0. And so our Hamiltonian simplified down to being equal to negative h bar squared over 2m times the second partial derivative with respect to x. But in reality, if we zoom back up, when we do have potential energy, it is included in the Hamiltonian operator, and that is why it is considered the total energy operator. Now, if we move on to the simple harmonic oscillator model, we can see that the potential energy operator, E potential of x, is equal to V of x, which we've seen before, and we showed in a few lectures ago that V of x is equal to 1/2 times the spring constant times the square of position. And that's for the potential energy operator in the simple harmonic oscillator model. The kinetic energy operator is equal to kinetic energy of x, which is equal to that portion of the Hamiltonian which we've become familiar with, except that our mass is now mu, which is our reduced mass. So it's negative h bar squared over 2 times mu times the second derivative with respect to x. So what we're going to do is determine the expectation values for total energy and for potential energy and for kinetic energy for a given system. And the system we're going to be looking at is the psi sub 1 wave function in the simple harmonic oscillator. And we'll be doing all of this in exercise 11. So, what are the average values for potential and kinetic energies for a quantum mechanical oscillator, which is what we call the simple harmonic oscillator, at n equals 1? So in order to do this, we need to consider the wave function for the simple harmonic oscillator at n equals 1. And that is given by this equation here, which is equal to 1 over root 2 times alpha over pi raised to the 1/4 times the quantity 2 alpha raised to the 1/2 times x times e raised to the quantity alpha x squared divided by 2. So the expectation value for total energy is given by this equation here, where we have our expectation value equation for energy, and so our energy operator appears in the numerator and it does not appear in the denominator. As we're going to see in the next page, this total energy can be separated into potential and kinetic, and that will be very useful for allowing us to describe the expectation values for potential and kinetic energy. Now, the simple harmonic oscillator wave functions, thankfully, are already normalized. We did that by including the a sub n normalization constant into our equation for the wave function. So these are already normalized, so we do not need to deal with the denominator because it's normalized already. So, given that we can separate potential and kinetic energy from the total energy, we can now set up and solve for the expectation value for potential energy. And this is going to require a few steps. So the first step is going to be to set up our formula. So our expectation value, which is our average value for potential energy is just going to be equal to the numerator of that previous equation, the integral from negative infinity to positive infinity of psi1, the complex conjugate, times our potential energy operator times psi1 of x dx, where v of x is equal to our potential energy operator. And so if we make a whole bunch of substitutions, we will get our full integral to be equal to the following. 1 over root 2 times alpha over pi raised to the 1/4 times the quantity 2 alpha raised to the 1/2 times x times e raised to the quantity alpha x squared over 2. That is our equation for the wave function at n equals 1. We are also multiplying by 1/2 kx squared, which is our potential energy equation, and then again multiplying by our wave function. Now what we're going to do is start removing from the integral any constants, and these will be anything that is not relative to x. So we're going to do this stepwise to make sure we keep track of everything. So first we're going to take out 1 over root 2 times alpha over pi raised to the 1/4, which appears here in this wave function, and then again when the wave function repeats. And when these are multiplied together, 1 over root 2 times 1 over root 2 becomes 1/2. Alpha over pi times alpha over pi, both raised to the 1/4, is going to be equal to alpha over pi raised to the 1/2. So these constants come out. And what we're left with is an integral of the remaining portions of the wave function, 2 alpha raised to the 1/2 times x times e raised to the quantity alpha x squared over 2 times our potential energy. What we're going to do now is take out the 1/2 k from our potential energy equation and leave everything else behind. And so this 1/2 k comes out and joins the other coefficients in front of the integral here. And now what we're left with is 2 alpha raised to the 1/2 times x times e raised to the negative alpha x squared over 2 times x squared, which is coming from our potential energy, times 2 alpha raised to the 1/2 times x times e raised to the quantity alpha x squared divided by 2. So now what we can do is combine all of our values for x that are appearing that are all just being multiplied by one another. And so x times x squared times x is equal to 4x. Meanwhile, our 2 alpha raised to the 1/2 is another coefficient that can be brought out in front. And when 2 alpha raised to the 1/2 is multiplied by itself, 2 times 2 becomes 4, and root alpha times root alpha becomes alpha. So now we have a whole bunch of constants out in front, and here is our remaining integral. And so now what we're going to do is combine some terms inside the integral, where we have e raised to the quantity alpha x squared divided by 2 times itself becomes e raised to the quantity negative 1 alpha x squared plus negative 1/2 alpha x squared. And so these add together just to give us e raised to the negative alpha x squared. Now let's put the integral off to the side for a second and see what to do about some of these constants. Well, we have 4 divided by 2 is 1, so our coefficients completely go away. Now our alpha exists here and then also as alpha raised to the 1/2. When we multiply these two together, we get alpha raised to the 3/2, which is the same as saying alpha cubed quantity raised to the 1/2. So this is going to be useful because that'll allow us to combine some terms. And so if we have alpha cubed raised to the 1/2 divided by pi also raised to the 1/2, we can put them into parentheses with one another. And so our constants out in front all simplify down to being just k times the quantity alpha cubed over pi raised to the 1/2. And now what we're left with is an integral x raised to the 4th times e raised to the negative alpha x squared. So now we're going to figure out how to solve this integral. And we're going to do that using a provided standard integral. So this shows up in the textbook in Math Essentials 2, and we're just going to allow this to be provided and see how it's used. Before we actually solve anything, I want to draw your attention to the numerator. So what's going on here is a series, 1 times 3 times 5 ... times the quantity 2n minus 1. What this means is we have a series where the maximum value that you're going to multiply by is equal to 2n minus 1. So for example, if n was equal to 1, then 2n minus 1 would be 2 minus 1, which is 1. And so our numerator would just be 1 times, that's it, 1. Because that is the maximum value that we have in the series. If, however, n was equal to 3, our maximum value, 2n minus 1, would be equal to 2 times 3, which is 6, minus 1, which would be 5. So then our numerator would actually be 1 times 3 times 5, because 5 shows up as being our maximum value. So what you have to do is multiply by every number in the series up until your maximum value. In this case, for n equals 3, that maximum value is 5, and so the numerator would become 15. Okay, so let's use this integral now, from 0 to positive infinity. So for us, we're taking the integral of x raised to the 4th times e raised to the negative alpha x squared. And so, if x raised to the 2n is going to be equal to x to the 4th, we can solve for n and see that for this integral, n is going to be equal to 2. For our maximum value in the numerator, 2 times 2 minus 1 is 3. And a simple substitution that this a variable that shows up in the integral, for us, that is just alpha. So that's a simple substitution. So let's use the equation. We have 1 times 3 times 5 up until the maximum value of 2n minus 1. Our maximum value of 2n minus 1 is 3. So our numerator is 1 times 3, which shows up here. Our denominator is 2 raised to the n plus 1. And our value for n is 2. So this is 2 raised to the 2 plus 1, which would be 3. And so our denominator is 2 cubed. N is equal to 2, and so in the denominator we also have alpha raised to 2. So this simplifies to being 3 over 2 cubed times alpha squared times root pi over a, which simplifies down to being 3 over 8 alpha squared times root pi over a. And so overall, we can say that our integral from 0 to infinity, as it's defined from 0 to infinity, of x to the 4th times e raised to the alpha x squared is equal to 3 over 8 alpha squared times root pi over a. So this standard integral is only defined as being from 0 to infinity. However, we're interested in solving our integral from negative infinity to positive infinity. So how does that change our answer here? Well, when we want to go from negative infinity to positive infinity, that is twice the range as 0 to infinity. So this range is going to be equal to the integral from 0 to infinity times 2. Because if we're starting from 0 going to positive infinity, that's only half of the range if we're also going from 0 to negative infinity. So we take our integral from negative infinity to positive infinity of x to the 4th times e raised to the negative alpha x squared dx. That's going to be equal to 2 times our answer, which would simply be 3/4 or 3 over 4 alpha squared times root pi over alpha. Now that we have solved our integral, we can bring that back and solve for our average value of potential energy, which is our expectation value. So our expectation value for potential energy is going to be equal to k, our spring constant, times alpha cubed over pi raised to the 1/2, all of these constants that were hanging out in front of the integral, times our integral from negative infinity to positive infinity of x to the 4th e raised to the negative alpha x squared dx. Now we have a value for this, and we just plug in. And so now we see that our expectation value is k times alpha cubed over pi raised to the 1/2 times 3 over 4 alpha squared times root pi over alpha. Great. Now let's clean this up. First, we're going to focus on cleaning up our alpha values. So alpha appears 3 times in our equation, And so we can clean it up as follows. So first we have in the numerator alpha cubed raised to the 1/2. In the denominator, we have alpha squared, and we also have alpha raised to the 1/2. And so in the numerator, we can simplify and say that we have alpha raised to the 3/2, and in the denominator, we have alpha raised to 4/2 plus 1/2. This simplifies to being alpha raised to 3/2 over alpha raised to 5/2, which simplifies to alpha raised to the quantity 3/2 minus 5/2, which is equal to alpha raised to the negative 2/2, which finally gives us alpha raised to the negative 1. We also have pi showing up in two places in our equation. That is nice and simple. We have root pi in the numerator, and we also have root pi in the denominator, and so those cancel with one another to give us 1. So overall, we can take the pi values out of this equation. Our alpha values simplify down to being alpha raised to the negative 1. So with these substitutions, we can find that the expectation value for potential energy is equal to 3/4 k times alpha raised to the negative 1, which is also a way of saying 3/4 k over alpha. Now, what does alpha actually equal? Well, as we've seen before, alpha is just defined as a bunch of constants. It's the square root of the spring constant times the reduced mass divided by h bar squared. So if that's what alpha is equal to, we have alpha in the denominator. So alpha raised to the negative 1 is just the reciprocal, and so that's going to be the square root of h bar squared over k times mu. And so if we plug this in for alpha raised to the negative 1, we will find that our potential energy is equal to 3/4 k times the square root of h bar squared over k mu. Now let's clean up our spring constants. We have two of them. We have k times k raised to the negative 1/2. That simplifies to being k raised to the quantity 2/2 minus 1/2, which is equal to k raised to the 1/2. We also have the square root of h bar squared, which is just equal to h bar. So if we clean this up further, we land with our final expression for the expectation value for potential energy, which is equal to 3/4 h bar times the square root of the spring constant divided by the reduced mass.